Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Hayley Beltz with us today. Hey, Hayley.
Hello.
Where are you located, Hayley?
I am in Ann Arbor, Michigan.
Ann Arbor, Michigan. All right. And has summer hit in Ann Arbor yet?
Yeah, kind of. Today's supposed to be really warm, but the next week we're supposed to rain every day. So a bit of a mixed bag there.
It's the upper Midwest. Yes.
Yeah.
We spent a little bit of time up there in my younger days. Very cool. So what is your current position there in Ann Arbor?
Yeah, I am I'll be a fourth year grad student this year at the University of Michigan.
Very cool. So you got maybe one more year?
Hopefully, yeah.
Right.
We'll see how it goes.
All right. Well, we'll have to do another video and I can refer to you as Dr. Beltz. So very good. That would be very nice. Very cool. So that is a pretty awesome home office there. Look like you have a pretty cool picture of a Skylab or something over your left shoulder there.
Yeah, International Space Station.
Very cool. Nice. Nice.
Yeah, I got that from Space Camp a few years back. So
good. Very good. Very nice. So Hayley, what do you like to do for research?
Yeah, so I study the atmospheres of hot Jupiters and ultra hot Jupiters, mostly through 3D numerical models known as general circulation models. And I also work a little bit with high resolution spectroscopy and the interface between that and the models.
So these GCM models, these are roughly the same things they use for Earth for predicting, Earth patterns, wind patterns.
Yeah, there's a lot of GCMs for Earth. For when we use it for gas giants, you have a whole different set of assumptions and different equations, of course, but you're still solving numerical equations in 3 dimensions and letting your atmosphere kind of develop with time.
Cool. And that is going to bring us to this very lovely AJ article. A significant increase in detection of high-resolution emission spectra using a 3-dimensional atmospheric model of a hot Jupiter. And Hayley, take us away.
Yeah, so the sort of goal of this work was to look into whether or not a 3D model could do a better job at getting a detection from high-resolution emission spectra. So most of the time when people do retrieval studies, based on spectroscopy of exoplanets, they have to compare the data to a simulated data, usually drawn from a 1-dimensional model. Usually people will generate hundreds or even thousands of 1D models of different metallicities, different species, different temperatures, and sort of examine the parameter space that way. But we know that planets are 3D, and so with this work, we were hoping to test whether or not we could use our 3D model without really any fine tuning, if that would do a better job than a suite of 1D models.
Okay.
So this work is focused on emission spectroscopy and is the complement to a previous paper by Aaron Flowers, who investigates this question for transmission spectroscopy.
Okay.
Since the two methods are pretty different and they look at different parts of the planet's atmosphere, it wasn't immediately obvious if emission spectra would also benefit from a 3D analysis.
Cool.
So we can kind of move to probably the first figure, and I can talk a little bit about the GCM. Okay. So it's a 3D numerical model that is double gray, meaning that it considers 2 different opacity regimes, a visible and an infrared opacity regime. And we set up a potential temperature pressure profile for the model and then let it calculate what it thinks the atmosphere is going to do based on a set of meteorology equations. Okay. And so in this first part of the paper, I'm setting up the GCM and showing that the hot Jupiter we're looking at, HD 209, is sort of the quintessential hot Jupiter to expect. So the parameters you're showing there on table 1 it's got an orbital period of 3.5 days. And so one of the things that we tested in this paper is whether or not, if we change the rotation period, if we can gather some information about the planet's rotational period. For hot Jupiters, we think that, or we expect them to be tidally synchronous, meaning that their orbital period and their rotational period are the same because they're so close to their host star. But that hasn't really been empirically constrained because it's difficult to do so, given how far away the planets are. And so we ran a series of 12 instances of our GCM with varying rotation rates with hot Jupiter-like parameters. And figure 1 there shows you the temperature structure near the infrared photosphere from our synchronous model. So this is the one where orbital period and rotational period are the same. So the color is showing you the temperature, and then the lines are showing you the wind patterns. And in this plot, it's important to note that the substellar point, so that's the point that's the closest to the host star, is at 0, 0, so smack dab in the center.
Okay, got it.
And so the important things to know about hot Jupiter atmospheres is that we see a really strong equatorial jet, which is shown in the winds kind of hovered around the equator. And what this jet does is that it moves the hottest point on the planet slightly east of the substellar point. So the hottest longitude isn't at 0, but it's around between 0 and 30-ish, depending on what pressure level you're looking at.
Okay.
And so this hot Jupiter is the sort of quintessential, no surprises hot Jupiter.
All right. Very cool.
And if we move down to table 2, that shows the different rotation rates that we measured. Okay. And so the rotational period directly converts to a rotational speed, but the max wind speeds aren't a one-to-one relationship between the rotational period and the wind speeds, because there's a lot of different feedback that happens. And so that's why it was important to actually run these models instead of just assuming that we could guess what the wind speeds would be. But we ran rotational periods between 2 and 9 days, and very much capturing the synchronous case as well.
I have a question. How far deep in the atmosphere? So where's your bottom boundary condition? So how far into the hot Jupiter do you go?
So we modeled down to 100 bars.
Okay. Okay.
Yeah, and especially down at those deep of pressures, that's not where any observational data is sensitive to. And so we're a little more hesitant to interpret the absolute bottom boundaries of the models, but it's important enough to get, below the radiative convective boundary and enough that you're not missing out on any of the upper atmosphere physics that are important.
Okay, great, thank you.
Yeah, and we can move on to figure 2, which is showing a bit of that equatorial jet in another way.
Okay.
And so what I'm showing here are longitudinally average east-west wind speeds as a function of latitude. And then the y-axis is showing pressure. So the top of the plot corresponds to the top of the modeled atmosphere. And the bottom is deeper into the atmosphere. And then this black line is showing you the boundary between positive and negative wind speeds.
Okay, yes.
And what we can see from this plot is that the equatorial jet, which is in the sort of dark blue at the center, is present throughout the majority of the atmosphere. It's strong, it's centered at the equator, and it's what we expect. And so that equatorial jet does a very important job in affecting a lot of the observables of the planet, which we can see in figure 3 right next to it. Okay. And so now we're looking at phase curves of our different models. We've got orbital phase on the x-axis, which is like a time, and then a flux on the y-axis. And then the gray dashed line and the gray parts beside it is the observational peak phase and the 1 sigma errors from it.
Got it.
And so what we can see from this plot is that 2 of the rotation periods are outliers compared to everything else, right? Those 2 at 9 days and at 6.9 days.
Yep.
These rotation periods are actually so slow that the equatorial jet doesn't form.
Okay.
And so because of that, their hotspot doesn't get moved and they peak much later in phase compared to everything else. And so from the phase curves alone, we could rule out these 2 rotation rates as unphysical or not agreeing with data. But all of the faster rotation rates all peak at about where it is, and those are in good agreement. And so we ran these GCMs, and one important thing to do after running the GCMs is we need to post-process them to generate some spectra. And if we scroll down to figure 4, one of the things that we really wanted to keep, that we made sure to treat very carefully, was line of sight velocities. Because the line of sight velocity is going to affect your Doppler broadening and shifting of your planetary lines. And so here is showing an orthographic projection of the upper atmosphere, so even higher than the previous temperature map we looked at. And again, the arrows are showing you the wind directions. The blue and red contours are showing lines of constant line of sight velocity, both blue shifted and red shifted.
Okay.
And that black dashed line shows you where line of sight velocity is 0.
Okay, I'm with you.
And so when we post-process these models, we carefully calculate the line of sight velocity, which is also related to both winds and rotation rate. And when we take that into account, we'll broaden the lines appropriately. And if we move probably to figure 5, we can start to look into the differences between our 3D model and a few of the 1D models we tried.
Okay.
So these are temperature pressure profiles, meaning that we're looking at different parts of the atmosphere, each temperature throughout the model.
Right.
So the rainbow lines correspond to points around the equator, and the hue corresponds to the longitude. And then the gray point shows us the temperature profiles from everywhere else in the model. And we'll ignore the 1D models for a second, which are in black. But some of the things we can notice from our 3D model is that at a single pressure level, there's a significant range in temperatures. Depending on the pressure level, over 700 Kelvin, which is very much not one-dimensional. We can see a difference between the day side and the night side, especially in the upper atmosphere.
Yeah.
On here, I'm also showing a few of the 1D models, including the best fit. And we can notice that the 1D models span the same sort of range in temperature and pressure, but are missing a lot of the features that are part of the 3D models. There's no day-night side difference, being a big one. And so the 1D models that we tested, we had a suite of over 700 of them. They varied in concentration of water and CO, as well as varying different lapse rates of the models, which decides the slope of the line between the 2 isothermal portions.
Okay.
And one thing to note here is that our best fit, the corresponding lapse rate is possibly non-physical. It's super adiabatic and expected to be steeper than we would think should be allowed physically.
Okay.
But since it's a 1D model, it has a lot of assumptions, maybe that's why it gives us an unphysical solution.
Okay. Okay.
And so with all that information, we can start to look at some of the spectra that we made. which can be found in figure 6.
Figure 6. Spectra. Very good. Let's pop that up a little bit. There we go.
So this is Spectra from our 12 different GCM runs over a very small wavelength range. You'll notice it's between 2.322 and 2.324. So this is R of 100,000, very high resolution and very small wavelength range, but still a lot of features. Each line corresponds to a different rotation rate. And the dashed line shows the normal unbroadened model. And then the solid line of the same color shows what happens when you allow the lines to be shifted and broadened due to wind and rotation. And so if we ignore the two slowest models for a second, we can see that when we include the Doppler effects, a lot of the features become very smoothed out. You lose a lot of sharpness in your bottom of your lines. It does kind of have a lot of broadening in it.
Yeah.
But our two slowest models, the difference between the Doppler broadened and the non-Doppler broadened are pretty small. And that's because the wind speeds are significantly less. And they're also a little bit in the westward direction, meaning that they actually counteract some of the broadening that you would get from the rotation of the planet.
Right.
And so because of that, those two look like outliers.
Mm-hmm. And they look like outliers on the phase diagram as well.
Yeah, definitely. And with the other spectra, besides those two slow rotators, once they're broadened, it's pretty hard to tell by eye the difference between them. There's a pretty similar level of broadening between the other spectra. And the reason this is we found out that in this regime, when you increase your rotation rate, your wind speed decreases a little bit. And so overall, that ends up with a similar amount of broadening for all of these rotation rates besides the two slowest ones.
Mm-hmm.
And sorry, go ahead.
I got the question. What are these lines from? Are these like from water or
so these are CO only. So these are all CO lines. Yes.
Got it. Okay. Very good. I'm with you. Okay, thanks.
Yeah. And so one of the things we wanted to sort of test would be whether or not theoretically could we estimate the rotation rate of the planet based on the broadening in the spectra. Mm-hmm. And so on figure 8, I'm showing several cross-correlation curves. And so what cross-correlation is when you have your data, which is I'm gonna represent by spectra on my hand, and you take your template spectra and you shift it in velocity space. Yes. And when it matches up, you get a high cross-correlation signal. And then when it doesn't match up, you get a smaller one. Okay. And this is done in high resolution spectroscopy because once you've reduced the data and everything, the planet signal is like hidden in the noise and you can't really actually see spectral lines when you look at the spectra. So instead, you use your template spectra, which maybe has tens of thousands of lines, and that allows you to get the detection that you couldn't have gotten from just looking at a particular line or two. And so in these cross-correlation plots, I correlate the Doppler off spectra with the Doppler on to sort of gauge how much the Doppler on broadens the spectra. Okay. The gray curve is sort of a comparison base point of just what an unbroadened spectra cross-correlated with itself looks like. So that's the base shape of the cross-correlation curve. Mm-hmm. And all the other colors is correlating the on with the off. Okay. And once again, we can see the two slowest rotators sticking out like a sore thumb. The slowest rotator almost looks exactly like the unshifted spectra. And that's again telling us that there's not a lot of broadening. All of the other rotation rates have a lower cross correlation peak, but are much wider in width.
Yes.
And one thing that was interesting that we found is all of the dashed vertical lines are dropping down from the peak cross correlation curve down to where it is in the velocity shift.
Yep.
And what we found is that there's not a huge Doppler shift in any one direction, neither blue shifted or red shifted. Some of them are slightly blue shifted, some of them are slightly red shifted, but there's not an easy trend with rotation rate or anything like that. So we can't use any kind of expected peak velocity shift to gather information about the atmosphere, unfortunately.
Oh, bummer.
And I think, let's go to figure 9 next. We're gonna jump around.
That's fine. No. Okay.
Okay, so this figure is definitely in the weeds, so I'll do my best to give it its justice.
Okay.
And so what I'm showing here is the width of the cross correlation on the y-axis as a function of the rotational period. And each rotation rate has 2 dots. It has the filled one, which corresponds to the full broadening, so including winds and rotation. Okay. And then the dot with a circle in it is the ones that only contain rotational broadening. So just from the rotation of the planet, not including the winds.
Okay.
And so we wanted to figure out if maybe the cross correlation width could give us information about the rotational period of the planet. But unfortunately, it's not that easy. We'll first looking at the right side of the plot with our 2 slowest rotators. These are the only 2 instances where when we include the winds, the cross correlation width goes down. Right. Yeah, and that's because those winds are actually in the westward direction and are counteracting the broadening from the rotation. Yeah. So those are kind of weird, and we can throw those aside for a second. With the other models, we can compare to this black dashed line, which is what happens if I take the temperature structure from the synchronous case and then artificially broaden it based on the different rotation periods. Okay. Okay. And so if there was a pattern where all of the other models were above or all of them were below, maybe we could deduce something there. But unfortunately, some models lie below that line, some models lie above that line. And that tells us that the overall broadening of the spectra is depends on a lot of things. The rotation rate and the winds don't have that nice, don't have a nice linear relationship or even monotonic relationship. No. And so because of that, some of our models end up being below that line and some of them being above. Right. And so this led us to deduce that we can't get rotational information out of high resolution emission spectra, at least these emission spectra, this rotation rate, which is unfortunate, but you know, it's still probably a synchronous planet. Mm-hmm. Right. So now let's hop back up to figure 7, and I can talk a little bit about the different chemistry assumptions that we used in our post-processing. So our GCM is double gray, and it doesn't, it assumes that the atmosphere is mostly hydrogen, which it is, but it doesn't make any assumptions about what the concentration of other species are. So that was something that we had to do in the post-processing step. And so for this planet, in the past, both carbon monoxide and water have been detected in its high resolution spectra. Water in particular, though, is notoriously tricky in high resolution, either from line list kind of info or other reasons, which made us want to do CO only models and then CO and water models. And we had two different assumptions about the concentrations then of those species. So one is sort of basic constant volume mixing ratio. We just choose one value and say, all right, here's what the volume mixing ratio is, and it's going to be constant for every temperature and pressure. And those values were informed by previous analyses on these planets with 1D models. The other type of chemistry assumption we did was assuming local chemical equilibrium based on solar concentration. And so neither of these methods of assuming chemistry are 100% correct, but they represent kind of two different extremes or things to try to see if one would be better than the other. And so if we look now at the actual spectra, especially the first three spectra at the top, so the brown, the purple, and the green, these all look very similar to each other. And the blue spectra actually kind of sticks out a little bit, especially in the center. You can kind of see a big difference between that and the other models. And that's because the blue model, the carbon monoxide and water in chemical equilibrium, had a significantly higher abundance of water than we chose for our constant volume mixing ratio. And so that affected the spectra drastically. And when we look at the detection significance, we'll see how that affects that as well.
Cool.
And so now I think we'll move to figure 10. Let's do that. And so what this plot is showing is that we detected the planet. I'm showing delta sigma contours from peak detection in different colors. So 1 sigma away from peak detection, 2, etc., as a function of planet rest frame velocity and orbital velocity. So that white star is where literature value puts that planet. And from this, we have our peak detection pretty close to the literature value. It's not on top of, but it's close enough for us to pretty confidently say, yep, that's the planet. We found it. Awesome.
Good.
And so now we can move over to table 3 to the left of it, this figure.
Table 3. Okay. And
so here is the sort of summation table of this work. These are our detection significances for all the different models that we tested. And so if we first look at the 3D detection significances, our peak detection was 6.87 sigma for when we included water and CO. And Doppler effects. And our best 1D model was only able to get a detection significance of just over 5 sigma. And so this was out of nearly 700 1D models. And of all those models, only 14 of them were able to return detection significances above 4 sigma. Compared to all but one instance of our 3D models. And so our 3D models definitely did a better job of fitting to this data. Some of the trends that we notice with our 3D models is that when we include Doppler effects, we have an increase in detection significance, depending, not a huge increase, but an increase across the board. And additionally, based on our chemistry assumptions, we can learn a little bit about water in this planet. So if we look at our chemical equilibrium models,
Mhm.
when we include water, the detection significance drops significantly by 2 sigma, over 2 sigma.
Yes.
Compared to in our constant volume mixing ratio, when we include water, we get a little bit of an increase of detection significance.
Yeah.
And so the way we interpreted that is that water is in the atmosphere of this planet, but at a significantly subsolar abundance. Our chemical equilibrium model had too much water in it, and that altered the spectra enough to make it be a worse match to the data.
Okay.
But the main difference in increasing our detection strength turns out to be the use of our 3D temperature structure. So Doppler shifts and chemistry assumptions made sort of secondary effects, but the big jump in detection significance was from including a 3D atmosphere.
Yeah.
We know planets are 3D, and we expect it to show up in their atmosphere, which it's exciting to see this at high resolution. That is, we start to show up. So that was cool to find.
Nice. That was awesome. Let me ask a question. What do you use for the radiative transfer to do the spectra?
Yeah, so it's a radiative transfer routine written by one of my collaborators, Eliza Kempton, and in this routine, we basically shoot hundreds of light rays through our model atmosphere and then calculate what the observer would see. So a little more complex than like a plane parallel assumption for radiative transfer. Yeah, we're able to include our entire atmosphere, the winds, speeds as well, and incorporate that to generate the spectra.
Okay, thanks.
Yeah. And so now we can go to figure 11. And so here I'm showing our best fit 3D model and several of our best fitting 1D models.
Okay.
And so the 1D models only have Doppler off versions because having winds in a 1D atmosphere is kind of hard to think about. But if we look at the actual lines, all the models have similar lines in the same place.
Yes.
But what differs a lot is the relative strength of the lines. And the relative strengths of the lines are really informed by the 3D structure of the planet, and is not something that can really be captured in 1D. And so this is why we're saying that the inclusion of the 3D temperature structure is what's driving the increase in detection strength.
Yes. Even though the lines are in some sense weaker.
Yeah, the lines aren't as strong, but the relative heights are what the really important factor is, and what's really making the difference in our detection strength.
Awesome. Cool. Okay.
And now we can move to figure 12.
Figure 12. Figure 12. Okay. Decrease that a little bit. Oops. Wrong one. Let's go there. Okay.
So yeah, so this is a long figure, so we'll just start on the left side and then look at the right. But so on the two plots on the left are showing our detection significance in the velocity space that we tested for our models with Doppler effects and without. And then the white star shows where the literature value of the planet is expected to be.
Yes. Okay.
And so looking at these, you can't really see too much, but if we look on the plot on the right, this is what happens when we subtract the two. So this is the preference for Doppler effects.
Got it.
So we have a positive preference for Doppler effects. It did increase our detection, but there wasn't a corresponding net shift in velocity space or anything. It wasn't because we assumed that there was a stronger rest frame velocity in one direction. And so how we interpreted that is that the way Doppler shifting was helping our detection was because of the line broadening more so than the line shifting.
Cool. Yep.
Yeah. And finally, we've got figure 13, which is our attempts to see if we could constrain the rotation rate based on the data. And so on the x-axis, we've got equatorial velocity, which will correspond to your rotation rate. And then the y-axis, I'm showing two different ones, orbital velocity and rest frame velocity.
Okay.
And so these contour plots aren't very constraining at all as of over the equatorial velocity space. If you're within 3 sigma of the peak detection, you've got the entire space covered.
Yeah.
So this tells us that we really can't constrain the equatorial velocity from the data in any kind of meaningful way. Yeah, and so sort of going back over the main points of this paper, because there's a lot of moving parts, but we found that this high resolution spectra is sensitive to the 3D structure of the atmosphere. For this hot Jupiter, our 1D models were almost 2 sigma less in detection from our 3D models, even though our 1D models were fine-tuned in so many different directions of parameter space. Additionally, in terms of increasing our detection significance, the biggest jump was from the use of the 3D temperature structure, but assumptions about chemistry and Doppler shifting did play a minor role in also bumping it up a little bit higher. And finally, there's water in this planet, but probably subsolar, at least based on this data.
Yes.
And yeah, so that's this paper.
Very cool. Hayley, I want to thank you very much for walking us through your article. Very nice.
Yeah,
let me ask, since you hinted at it a couple of times, and just where do we go as a community, let's say over the next 5 years? Are there, is it worthwhile doing even higher resolution calculations? Is there new observations coming online in the near future? And just sort of where are we going in this field over the next 5 years?
Yeah, so I guess I'd like to say that 3D effects are important, and especially as we get to higher resolution, they seem to be getting even more important, especially for these planets like hot Jupiters and ultra hot Jupiters, which have such different day sides and night sides. These 3D effects are there, and we should take account of them, or else we might bias our interpretations of data.
Very cool. Good. So looking forward to some new observations, maybe from the extremely large telescopes, or maybe JWST or something along those lines can be able to hone in on some of those.
Yeah, and I'll do a little plug. I've currently working on a paper about ultra hot Jupiters with our GCM, which is very exciting, including the effects of magnetic drag. So be on the lookout for that scary magnetism.
Cracks me up. Scary magnetism. Very good. Yeah, well, I look forward to seeing that article in the AAS journals. So very good. So Hayley, thank you once again. Thank you, everyone, and we will see you on the next one. Bye-bye.